Right. So last time we talked about the human visual system. How do people actually perceive images of the natural world, right? How does the retina work, that kind of thing. So, I mean, that was at a very high level, obviously. And we don't want to spend too much time on that because what we really care about is how do digital images work in computers, okay? So what I want to talk about today is kind of an introduction to kind of how does a camera work, and then what are the fundamental camera parameters you need to be aware of when you're taking a digital image, okay? So I think that actually, Adam Sandler said it best. It's all true. Okay, so let's talk about sensing. Okay, so typically the first thing we need to do is have a CCD, or a light-aware sensor. So this is really the kind of thing that, I'm not an expert in terms of how it actually works, but fundamentally the idea is that we have a kind of a little window through which light energy is collected. So energy comes down in this way. And there's a filter that basically selects, for example, for a certain color, right? So we talked about last time how our eyes are sensitive to roughly red, green, and blue light, although we saw that from the cone responses that's not actually 100% correct, but fundamentally in that range. And the filter acts to kind of pass certain frequencies or certain wavelengths of light through. Then we have some sort of a cavity with some sort of a sensing material. And then what comes out of this little sensor element is basically a voltage that is proportional to the incoming light. Right? So a common way of doing this is to think about this like a photodiode, right? Something that you put a filter on top of a photodiode, you stack these together into an array, and that's what gives you your pixels, okay? And so, like I just said, usually we have many, many, many such sensors in a camera. And so usually sensors are arranged in an array. So, for example, in almost every instance we're going to talk about in class, we have a rectangular array of these sensors, which form pixels. But it's also common to have just a single strip of sensors. And so these kinds of systems are very common in things like flatbed scanner, right? You put a page on the glass plate, and then there's something that kind of runs across the width of the page, and there's really only one line of sensors that goes across the page. Same kind of thing with like a photocopier or a fax machine. And another instance where this is used a lot, actually, is in things like airborne scanning. So you might imagine that you have a airplane. Again, I kind of see how well I can draw this here. So if I have an aircraft that is surveying some terrain, it may be doing so with basically like a moving stripe on the ground that is picking up, responses as the stripe moves forward. Or we talked about how in a CAT scanning scenario, if you have a patient and the patient is surrounded by this CT ring, that fundamentally what's happening is you're getting a strip of responses from rays that pass through the patient. And so, again, in that case, you're not acquiring the whole image at once, you're acquiring one stripe. And as this patient is moved laterally through the ring, you acquire information from the whole body, right? Okay, so we're going to kind of assume most of the time that our pixels are arranged in a grid, that we get them. We don't really actually care that much about how it happened, but this is just telling you the basic idea of how it works. Okay. All right, so how do we get from this to the actual image? Okay, so kind of the setup is that we have some object in the outside world, right? We have our camera, and then we have our CCD. Okay? And the simplest model for how the image actually gets formed on the sensor is what's called pinhole image projection. Okay? So the idea is that if you imagine that there is an infinitely small hole, which is basically like the camera aperture, rays of light are reflected through, so if I have this point on the tree, rays of light pass through the pinhole and impinge on the sensor. And consequently, what appears on the sensor is like a tiny upside-down image of what I'm looking at. Okay? And this allows us to figure out, if I've got an image that is, or if I've got an object in the world that is, a certain size, how big is it going to appear on the CCD? How many pixels will it take up? And the answer to that question is fundamentally related to similar triangles, right? So here's the idea, is that you may have heard that a camera has what's called a focal length, okay? The focal length is the distance between the hole that lets the light into the camera and the location of the CCD, right? So again, the focal length is a very, very small number, right? Certainly measured in the millimeters, right? And I can imagine that, say we're looking at this point on the tree that's basically straight through the middle of the sensor. Let's call this distance here Z. Okay, so this is the focal length. And then I want to know, how high does the tree appear to be on the physical CCD sensor? Well, I can say, okay, let's call this height here X, big X, and that means that the height of it on the little CCD is little x. And by similar triangles, right, I can say this angle and this angle are equal. So that means that, little x, or let's say this, big X over big Z is the same as little x over little f. And that means that if I know the focal length and I know how big stuff is in the world, that my little x is equal to f times big X over big Z. Okay? So this is the world. This is the image plane. And the idea is that, in terms of measuring things, I assume that the pinhole of the camera is located in the world at like 0, 0, 0 coordinates, right? So I can measure the distance from this point as capital Z and the up and down as capital X. And of course, this really works in 3 dimensions too. So kind of a better picture of this is on this PDF, right? So this is, for example, this is just a picture to show how points in the scene pass through the camera center and impinge on the image plane. You can see from this picture that actually everything on the image plane, just like in your retina, is upside down, right? And so the camera is going to flip that over before it passes it to you as an image. Another way of thinking about this problem is that you can kind of imagine that the image plane is between the aperture and the world, and that way things seem to be right side up. That's what this right-hand picture is. But here's kind of a picture of, again, how the geometry works, right? So I've got the image plane here in gray. That's like the camera sensor. And I imagine that I'm pushing from the origin through the image plane out into the world. And I take a coordinate out into the world that has 3 dimensions, and I project it onto the image plane, which has 2 dimensions, via these similar triangles. And the similar triangles here are illustrated again, where little f is to big Z, as in this case, little y is to big Y. So again, let me just restate this to make it really clear. So we have a point here in the world coordinates, by which I mean this is a 3D point in the world. We assume that the camera pinhole is at 0, 0, 0, and then the projection of capital XYZ onto the image plane is little x, y, where little x is equal to f times big X over big Z, little y is equal to little f times big Y over big Z. And that all comes out of similar triangles, basically. And, you know, I'm not going to make it any more complicated than that. I mean, one thing to notice, actually, is that any point along this ray, right, will get projected onto the same point on the CCD. So in some sense, when I send rays out into the world, they are going to hit the first thing that they see, and that's what gives the image, you know, coordinate its color. And, you know, that's mostly true, although there are certainly more complicating factors, like if you have a transparent object that the light ray passes through, well, then maybe I have some color that comes from the transparent object and then some color that comes from what's behind the object. We're not going to go into that kind of detail. But the main thing I want you to get at is the geometry, okay? And so this basically will tell me now on the CCD array that if I imagine that this point here is 0, 0 in the middle, that will tell me where little x, little y is, okay? We have to still think about, though, what are the units of everything, right? So the world is measured in, say, meters, right? And when I do these ratios of capital letters, the units cancel out, okay? And little f is usually measured in millimeters, okay? So that means that when I finish this computation, I'm going to get a little x, little y measured in millimeters, and that's not the same as pixels, right? So in order to convert that to the pixel grid that I have in MATLAB or in Photoshop, I need to do one more conversion that basically tells me, you know, how many pixels or how do the pixels fit onto the CCD array, right? And so typically a CCD array you may find, you know, is pretty small. So for example, 6.4 by 4 millimeters is what's called a half-inch CCD, and then 4.8 by 3.2 millimeters is what's called third CCD. And you can find that, let me see here, right? You can find pictures like this that kind of tell you how big the CCD array is on different systems, right? So it used to be, right, that if you had a old school SLR analog camera, 35 millimeter camera, that's what they call basically like full frame, which is, you know, a pretty big thing. That was like a 3.6 centimeter by 2.4 centimeter thing. That's how big your film negative is, if any of you ever actually used film in your camera, right? So that was a big chunk of thing. You compare that against, for example, what your iPhone is working with. That sensor is much, much smaller, right? It's basically 4.5 millimeters by 3 millimeters. And so in some sense, you know, when you're talking about photography, you generally want to have as much light onto the CCD array as possible. You have a lot of light gathering ability, and you want the effective pixels to be kind of getting as much light as possible. And so in general, if you're a photography person, you will think that having a bigger sensor is better, right? That's usually the first thing that you look at when you're buying like a DSLR. I have one of these like mirrorless cameras. So I have an Olympus mirrorless camera that is not as big as a full frame, but, you know, almost as big as like a Nikon DSLR, which is a pretty good size. Question? Yeah.
Where would an IMAX camera fit on this?
So an IMAX camera, that's a good question. I think the IMAX camera frames are very large, right? Because I remember going to a museum like and seeing they have, sometimes you can see the IMAX reels, and if I remember correctly, that's pretty thick. I mean, I guess we could, if I'm online, we can Google it. So size. Let's see what. So this is 70 millimeters, which is pretty big, right? Crap. So, I mean, the platters are big. Where does it tell me about the size of it? I think it's pretty, oh, here we go. Film frame dimensions of basically 7 centimeters by 55 centimeters. That's pretty big, right? Of course, the reason for that is that IMAX movies are getting projected like hugely, large, right? So that's probably one of the biggest film stocks that you could probably find today. I think the only other thing that is kind of rivaling that in size is if you have any friends who have like a really old school like glass plate camera, like the ones that you used to see the old-timey photographers with, those had really large negatives, right, where the negative was like a big plate like this. So it's in some sense, I just saw a very interesting talk by Steve Seitz, who is a professor at University of Washington and also now works at Google. And the talk was called The Death of the Camera. And it was actually pretty interesting, basically saying that obviously we all know that digital cameras killed off analog cameras in large part due to how convenient it was to take pictures and immediately share them and process them. But now hardly anyone uses handheld separate camera, right? Like many people now just use their smartphones, right? In some sense, it's kind of depressing to think that you're throwing away the quality. Like certainly analog cameras in some sense were kind of really good compared to the early digital cameras. And digital cameras now, the ones that you would hold in your hand, are comparatively better than your iPhone camera. But apparently the sales of like point-and-shoot cameras has just plummeted, and they are on their way out, right? And so the premise was that at some point we're going to throw away all of our special purpose cameras and just use our phone, and we're going to trade off the quality that our phone is able to give us with more sophisticated digital image processing and computer vision to improve the image after we took it, right? So for example, Google just released this refocusing algorithm. I guess I'm kind of getting off topic here, but I guess while we're here. So let's see here. I'm not sure if I can find it on the top of my head, but could be this one. Okay, I don't know what's happening with that woman there. It was, all right, I'll have to see if I can find this blog or this post afterwards, because it's kind of cool. Basically, it shows that you can take the image that you've got and you can refocus it after the fact. Let's see if this doesn't. All right, I'll post something to Piazza once I find the link that I'm looking for. But basically, the idea is that one thing that you really like if you're a professional photographer is this notion of depth of field. And the idea is that if you take a portrait, right, you want stuff that's close to the camera, the person that you're shooting, to be super in focus. And then it strikes us as a pleasing picture if the background is kind of out of focus, right, where it seems to pop if the person is more sharp than the background, right? And it's hard to get that nice depth of field with a tiny sensor and a tiny focal length. And you need a real camera to be able to really do that. And so the idea is that you could hallucinate that depth of focus after the fact, or that depth of field after the fact by, for example, incorporating like a little range image into your camera that bounces infrared light off the subject and figures out how far away they are, and then you can say, okay, far away stuff should be kept in focus and I should automatically blur the background, right? So this actually might be an interesting little, as a project for this course, investigating and implementing those kinds of ideas might be good. I think that, you're definitely hearing about devices now, like the Google Tango phone that is coming up, that have range sensors in them. Apparently the way that the Google one works is that you move the device physically a little bit when you take the picture, and then by looking at these multiple images, you can kind of compare pixels. We'll talk about that a little bit maybe towards the end of class to figure out how far away things are, whether they're close or far from the camera. So we're kind of entering the era of computational photography instead of kind of light, rays and geometry type photography. Question? Comment? Yes, so Lytro is another thing that's kind of interesting. So Lytro is, we have one in the ERC. It's like a little camera about this big, and instead of having a single lens that focuses light on CCD, it has, hundreds of micro lenses, right? And the idea is that what you're getting is images of the scene that are all from slightly different angles. And that's another way that you can refocus the scene after the fact, because you've got, it's kind of like the effect of having a bunch of little cameras where I've stepped, a small amount. I'm basically like moving the aperture around effectively, right? And having all that extra information allows me to do some refocusing. And that, again, that's kind of a neat effect where you can have kind of a slider that says, what do I want to be in focus, everything or just the front? Right? So, yeah, so that kind of stuff is really cool. And like I said, there are definitely courses popping up and research areas in this era of computational photography where, for example, one thing I didn't mention, and I don't want to get into it too much, is that this model of light passing through an aperture works surprisingly well for the kinds of images that we create, right? And in some sense, this was known a long time ago, right? Like if you've ever been to an art installation where someone like drills a hole in the side of a barn in the middle of nowhere and then puts some sort of like, you don't even necessarily need photosensitive paper on the back wall. You can basically let the light come in and you will see this upside down image of the outside forming on the wall opposite where you drilled the hole in the barn, right? That's basically very crude pinhole image formation. Now, real images and real cameras are generally acquired with lenses, right? And so lenses are not really part of this equation, but it turns out that you can model a lot of lens stuff with a simple correction to this term, right? There's a lens distortion model that basically says that you probably have seen, kind of barrel lens distortion where things seem to be kind of bowed out from the center, and then there's something called pincushion distortion where it's kind of bowed in, right? So you can kind of incorporate lenses and stuff into this model, but there are some very smart people who are doing even more advanced things where you could say, okay, instead of having this be a circular hole, you could put like a binary pattern, like a black and white checkerboard pattern of random black and white squares, and you could flip those black and white squares on and off. It's what's called a coded aperture. And it turns out you get images that don't make a lot of sense to humans, but turn out to give you a lot more rich information about the state of the world. That's kind of like the kind of thing that we would talk about in more like a computer vision course after you've gotten a little bit more than just the pure basics under your belt. But just to say, there's a lot of cool stuff related to the physical acquisition of things and the processing of light. Okay, so I got way off track, but other comments or questions? It's nice to have a discussion about this stuff. Yeah?
One thing they did was having a second tinier lens right next to one, so that they could depth perception that way.
So through the same optical
No,
path?
they had one lens, and then right next to it they had a smaller camera to try to
Right,
take it
yes.
twice as long.
Yeah, to be able to do any sort of like kind of depth perception, you generally need two optical pathways, two lenses, right? So, yeah, that's kind of where the future is, right? So, I mean, definitely you're going to see that the next generation cell phones have multiple such sensors. Okay. So let me just get back to this before we all forget it. So basically the idea is that I have my CCD array, which is really fundamentally some tiny thing measured in units of millimeters. And then this array is split up into, and this is very crude, into pixels, right? And so this is where you get this kind of notion of image resolution and megapixels, right? And so, for example, an image, kind of an older image might be 1600 by 1200 pixels, which means that there are 1600 little sensors crammed into here and 1200 little sensors crammed into here. And if I multiply these things together, I get about 1900,000 pixels, which is kind of like what you would call 2 megapixel. And so, again, this is like a photography debate, right? You don't want to just go for the camera that has the largest number of megapixels, because if the image sensor is not very big on the camera, for example, then every one of those pixels is effectively gathering less light. Kind of what you want to look for first is the size of the physical sensor, and then you worry about how that sensor has been divided into pixels, right? And so kind of typical pixel resolutions, it changes day to day, right? I mean, I remember when I was first doing image processing work as a grad student, I had one of the first kind of consumer digital cameras that you could buy in my lab, and I think that was like a 320 by 240 digital image, or it could have been even smaller, right? So really, really tiny images. And of course now, in some sense, resolution is no problem. Like you can get like, easily your GoPro, right, I think can probably record 4K, can it, or maybe 2K, like, which means 2,000 pixels or even 4,000 pixels wide. So, you know, one thing to remember, though, that you may not know is that megapixels is also not exactly the best or the most obvious measure of the quality of an image, because it turns out that most digital cameras use, so we have to come back and talk about color, right? So we want to acquire the red, green, and blue values of all these points at every pixel. So when I open up an image in Photoshop, I get RGB at each pixel, right? But it turns out that actually the pixels in most digital cameras are kind of the pixel color responses are usually arranged in a what's called Bayer pattern. And what that means is that the responses of the pixels, it's not like I get a raw reading of red, green, blue at every pixel. It turns out that every pixel in the digital camera has basically only one actual color reading, either red or green or blue. And typically, they're arranged in this way. So you can see that we talked last time about how the human eye is most sensitive to green. And so that's why half of the pixels in this Bayer pattern are green, and they're on these diagonals. Then a quarter of them are red pixels, and a quarter of them are blue pixels. And that means that when your digital camera gives you back RGB, it's doing what's called demosaicing, which means it's kind of filling in, it's hallucinating, you know, the other two channels that it didn't actually physically acquire at every pixel, right? So while it's true that there are some super up-and-coming cameras, there's a system called Foveon, apparently, that is more like this, where actually it has, basically, they call this the direct image sensor, where every pixel is actually acquiring red, green, and blue at every pixel. That's typically not the way that your, you know, digital camera that you probably own yourself is going to work. That may be true for very high-end stuff, but for most of the time you're going to have this so-called Bayer array. And so here you can see kind of the pattern of the blue responses, the green responses, and the red responses that you get. And so that means that the camera has to decide, okay, so if I have a, you know, if I have a response like blue, so if this is kind of like my Bayer pattern, and then I have green, red, green, red, green, red, blue, green, blue, green, blue, green. Right, so if I want to know, for example, here I know the R exactly because the sensor captured that. If I want to infer the green, maybe what I would do would be to average these 4 green pixels together to get the green at that point. And then to get the blue, maybe I would average these 4 diagonal blue channels, right? And so basically, this process is called demosaicing. Okay, so that's the basic image geometry, image formation, image sensing part that I wanted to talk about, right? So now you should be able to say, okay, if I've got a camera and I'm 100 meters away from the scene and my focal length is, you know, 3 millimeters, you know, and my CCD size is split up into, you know, 1920 by 1080 pixels, then where does this point XYZ in the 3D world project as a pixel value, right? And that's one of the homework questions, is just doing that geometry. So first you have to do this pinhole projection equation, then you have to decide how to convert the physical units on the CCD array into pixels, right? But that's fundamentally how the process works. Okay, so any questions or comments about that kind of stuff? Okay, so let me say a little bit more about kind of light response, just a couple more comments. So if any of you have taken a computer graphics course, for example, I just want to talk a little bit about the illumination model of how things work. So kind of the first, you know, the first picture I showed was something like this, right? Energy coming onto the CCD array. So how much light energy is actually reaching this array depends on what's going on in the scene, right? So you have some object in the scene, and I want to know how much light is arriving at this point on the image plane. Okay? And so usually I have some sort of an illumination source. And so this could be the sun, it could be a spotlight, it could be, light that's being emitted from a glowing object. And so the idea is that, light from all the sources of the scene is bouncing off the object, and then some of that light is bouncing into the image sensor. And so this little region of the object, right, which I'm going to call like a scene element. So the amount of energy, the amount of light that gets recorded on the sensor is a combination of both the strength of the illumination source and the kind of inherent color of the object, right? So for example, here, the illumination source can have kind of, in some sense, infinite, brightness, right? So here this is kind of saying how many lumens per meter squared, right? So for example, I'll talk about the ranges of those kinds of illumination sources on the next slide. And then the scene element has some sort of inherent reflectance. That basically is a measure of how shiny the object is. And then fundamentally, what I receive at this point on the sensor is the product of the illumination source and the reflectance. And this is really highly simplified, right? This is kind of assuming that the color or the intensity at one pixel is only coming from one point in the scene. But that doesn't take into account things like shadows or multiple illumination sources or transparency. I mean, all that stuff is required to really accurately build a model. So if any of you have done like your own simple ray tracer, for example, like one of the first things that you do in a computer graphics course is to build a simple ray tracer that takes 3D geometry, a camera location, and bounces light rays off. And so the first thing you realize is that the image looks really unnatural unless you take into account multiple bounces of light, and so on. So this is the crude model for what happens along each light ray. And I just want to say a little bit about the fact that, okay, so how bright can illumination sources be, right? So, for example, there's a pretty wide range. So if I have like a clear sunny day, that's about as much light as you can imagine naturally coming into the world. And so that turns out to be about 90,000 lumens per meter squared. A cloudy day is a little bit dimmer, about 10 times less. Indoors is another order of magnitude less. And about as dark as you could imagine seeing stuff like the full moon is a couple orders of is another order of magnitude lower. Right? So kind of you could imagine that in our natural world, we kind of range between the 90K in the brightest possible situation to the full moon, which is about 100 lumens per meter squared. And then in terms of how reflective objects can be, so again, that's a number between 0 and 1 that says how much of the incoming light is bounced back to your eye, right? And so, for example, we all know about snow, right? So snow is about as, reflective as you can get, right? So much light is reflected back from the snow into your eyes. Like a flat white wall, like the ones in this room, probably have a reflectivity of about 0.8. Stainless steel, like your dishwasher, if you've got a nice dishwasher, is about 0.65. And then something like black velvet, which seems to kind of suck all the light out of it, right, has a very low reflectance of like 0.01. But anyway, this is kind of like the telling a little bit more of the story about how much light actually shows up on the CCD sensor is, again, this complicated combination of stuff coming from the world, the properties of the objects that are being imaged, and the sensitivity of the sensor. Yeah?
Where does water fall on this? Like if you're on a boat?
If you're on a boat. So water is a little bit, again, one of the things that's probably not going to follow these rules exactly because, a ray that bounces off the surface of the water, almost could act like a mirror in some situations, right? So in some cases, you're getting light rays that are bouncing directly off the water into your eye or into the sensor that, it's almost like looking into a mirror, right? But then there are other cases where you're looking at the water surface at a different angle and you see through the water into stuff that is, inside, which means that the light rays that are coming in a different direction are totally absorbed and never reflected back to you, right? So, yeah, water is extremely tough to model, what you see through, right? Yeah, that's really hard. You wouldn't ask your, first year computer graphics student to ray trace water, right? Because it would be like a nightmare. So, other questions or comments? Okay, so one thing that would be familiar to you guys from signal processing is notions of sampling and quantization, okay? And these issues maybe were a little bit abstract when we were talking about kind of generic digital signals, but in images they're really concrete, right? So let's talk about sampling and quantization. So kind of like the pictures that we drew in signal processing and like signal systems in DSP, were along the lines of this. Let's suppose we had a function of x. So sampling is basically saying that I don't get continuous samples of this function. Instead, what I get are discrete samples like this. So, this is like delta x, 2 delta x, 3 delta x, and so on. So we know from, don't worry about it, we're not going to talk about too much of this class, but we know from things like Nyquist theory and so on that if we sample these, if we sample these functional samples close enough together, we can reconstruct the continuous function, right? So we're not going to talk really about ideal function reconstruction in this class, but the same idea applies because really what I get in my digital image are a series of discrete pixels, right? We really don't have any sort of continuous world when it comes to real-world image processing. It would have been true if we were talking about the kind of image that's produced on film, right, where there really is no sense of discretization. But in terms of digital images, we have these rigidly boxed-in pixels, okay? The other thing that's important is that on this axis, I may not actually be able to represent the intensity or the color of a pixel with what you would call floating point precision. So instead, the samples that I get are actually kind of rounded to the nearest quantization level, okay? And so that means that the measured light intensity on the pixel is not exactly the energy it's arriving at the sensor, it's been quantized, right? And so, again, we talked about that a little bit in DSP in kind of an abstract way. I guess we talked about it maybe a little bit in the context of audio processing. In image processing, it's much easier to understand and observe the effects of sampling and quantization. So let's take a look, for example, I put together a demo. So again, at the end of this, I'm also going to talk a little bit about MATLAB-y stuff. But so here, when I read in an image, I can see that this is already a grayscale image, and I can use ImShow to look at it. Okay, so here's this picture. Now, I wrote a little function to change the sampling and the quantization of this image. Okay, so this is not a built-in function in MATLAB. I wrote it myself. Okay, so what you're going to see here is, let me see if I move this down. So at the top bar, and again, you can see this a little better on the video, you can see it says pixels are 1 square and there are 256 gray levels, right? So this is basically the innate original resolution of the image. And so what I can do first is change the resolution. Okay, actually it goes this way. So here what I'm doing is I'm basically making the pixels larger, or making things blockier. Right? So this is kind of like the effect of saying that if I had a lower quality image sensor and the pixels on the physical CCD were bigger, what would the resulting image look like? And so the manifestation of that is that as I make the pixels larger, things seem to look blockier and blockier, right? To the point that, you know, at some point you can't even tell what's going on in the image, right? So you might argue that, you know, I could go 1 unit down and still be able to read the text, but another unit down and I wouldn't be able to see what's going on. And of course, you know, even further, then only kind of large details of the image are left. Maybe you might be able to pick out the word dwarf and the fact that this is a parking arrow. Maybe certainly at this level you could, but you couldn't read any of the text, for example. And so, you know, this is effectively the pixels being 8 units bigger than they were in the original image. Okay, so certainly the kind of resolution has a huge effect on the kind of usefulness of an image. The other thing that we can do is change the quantization levels. Basically, how many gray levels am I using to represent the image? And so in this case, this is an image with 256 gray levels, which is pretty standard. We call this an 8-bit image, right? And so now I can change the number of gray levels, which means I'm kind of rounding the pixels to, you know, fewer and fewer levels. And so when I round from 256 to 128, I don't actually see that much of a change. It looks about the same. Now I'm going down to 64 gray levels. The change from here to here, again, is still not super perceptible. 64 to 32, now things are starting to happen. And let me just take it all the way down so you can kind of see the effect. So if I go all the way down, this is like only using 2 gray levels. Fundamentally, a dark gray and a light gray, right? And so again, this is not horrible in the sense of image, like I can read the words, right? So if I have a high contrast image, I may still be able to get something out of it, but this is 4 gray levels, 8 gray levels, 16 gray levels, 32, and so on. So there is kind of a sweet spot that you might say that you might be able to reduce the number of gray levels to some number that's lower than 8-bit and still think the image looked okay. One thing that you start to see, and I'm just going to turn the lights down a little bit for this, is I want you to look at the upper right-hand corner. So this is the original. What you're going to see is what's called false contouring. And so here, originally the cloudy area of the upper right-hand sky is kind of like a nice, continuously changing gray level. As I change the quantization, you start to see here, for example, that there is some what you call false contouring, right? So now it looks like there's a band of, there's like a circular dot of light pixels, then there's a kind of an aura of a little bit darker, then there's a little bit darker. So you start to see, and if I pick it down even more, you start to see it even more. You kind of see that what used to look like smooth, continuous changes in grayscale now look like blotchy rings of what are called false contouring. And you see the same thing on the sign, right? So even though the original sign looked like maybe it was roughly the same color, as I kick down the number of gray levels, you can see that, you know, the camera response is saying that this area is a little lighter than the area around the text, and you start to get this kind of contouring on the sign also. And here the false contouring is really bad. And actually, here's a good example where you can see it on the corner of this post, right? And this is actually kind of a nice manifestation of the way that light hits real surfaces, right? So if I have a ball in the scene, I expect this kind of fall off where the intensity of the ball is going to be brightest, where, you know, so the sun is probably over where my hand is, it's coming down and hitting the ball, and that's where the brightest thing is. You can kind of see the rings of bright to dark intensity that, you know, here if I pick it up a little bit, you can see that it starts to go back to a nice smooth gradient. But as I bring it down, you can actually kind of perceive, maybe you could even make some inferences about the direction that the sunlight was coming from in the scene without knowing anything more about it, right? So that's kind of cool. Okay, and so one of the things I wanted you to do on the homework is to basically do this experiment yourself, where you make an image in MATLAB. That's one of the earlier problems, and then start to kick down the number of gray levels and see the visual impact it has on the image. Okay, and so just to write down a couple of points from what I said verbally. So frequently, we basically, we often use 8 bits, which is the same as 256 levels per color channel. And so that means that if I have a, red, green, blue image, I have, 2 to the 8th red, 2 to the 8th green, 2 to the 8th blue colors, right? And that would still be called an 8-bit color image. And so, again, you guys are probably like well beyond this era of computing, but it used to be that in Microsoft Windows, there was like a little drop-down box that would say, how many colors do you want your display to be, right? There was like 16 colors, 256 colors, and there was one that was called millions of colors, right? And that was really fundamentally this, right, where you say, okay, that's about as good as you can get. Now, it's true, and we'll talk a little more about like image file formats later in the class. It's true that there are some ways of storing images that use more than 8 bits. So, for example, the TIFF standard has, I think, an option to have like 16 bits or maybe 12 bits of color, right? But for the most part, if you download an image off the web, a PNG or a JPEG, it's going to have 8 bits of color in every channel. Okay, so the lesson is that the lower the sampling rate, which is kind of like the lower resolution, that leads to blockiness. And the lower the number of levels, that leads to false contouring and kind of just general lack of detail.
Is there a term for the number of levels? I mean,
You call that the bit depth, I would say. Yeah.
sampling rate versus bit depth.
Yeah, sampling rate versus bit depth. Yeah. So other comments or questions? Okay, so let me just say a few words about, I think I mentioned this last time, but it's a good place to say it again now that we've talked about how images are formed. Most of the time in this class, we think of an image as a 2D array of numbers. And I'm gonna tell you right now that even though we talked a lot about color last time, that a lot of what I do in the development parts of this course, I'm going to show you basically on grayscale images. Part of the reason being that it's easier to explain things as a function of this one number, which is the grayscale level, instead of just doing a for I equals 1 to 3 loop around the 3 color channels, right? Fundamentally, a lot of color image processing is just like doing the same thing on each of the color channels. And so it's often easier to explain things just on a grayscale image to show you the concept. And if you want to make it work on RGB images, it's pretty straightforward to do. So there is sometimes a little bit of a, disconnect when you're thinking about naming matrix elements, right? So I think we could all agree that this is like the 1-1 element of the matrix, and then I would call this the first row, second column, first row, third column, and so on, right? And so this is basically the standard way of talking about the entries of a matrix. And so usually X is going to refer to the row, and Y is going to refer to the column. The problem with this, unfortunately, is that that means that this is the direction of increasing X, this is the direction of increasing Y, and we can run into problems when we start to talk about things that are more like in Cartesian coordinates. Right? So if I'm talking about, plotting a graph of a calculus function, we always said X was this way and Y was that way, right? And so this can cause some confusion sometimes, and I will do my best to let you know when we're entering a period of confusion, but just be aware that this can happen, right? So especially, some of the more mathematical stuff, right? So at some point we're going to talk about, for example, what is the two-dimensional version of the Fourier transform, right? And the Fourier transform is something that's very mathy, right? Very continuous time thinking. And so it's easiest to talk about the Fourier transform in the world of Cartesian coordinates. But then we have to change our thinking back to how should that work when we bring that back to MATLAB. So again, I'll do my best to try to head off that confusion. Another sometimes source of confusion is, again, and this is kind of just like a MATLAB thing, that those of you that are programmers or C people would probably want to call this the 0, 0 element of the image, but we're going to stick with calling that the 1, 1 element of the image because we're going to mostly think about MATLAB. A bigger problem along those same lines is that there are some cases where it's more convenient to think about the center of the image being 0, 0, and some cases where it's more convenient to think about the 0, 0 being at the upper left. And so, again, I'll try to be clear about when we need to use each one of those things. So for example, when you talk about image, so let's go back to that for a second, talk about the image formation, right? So here, and to some extent here, right? So here, this is implicitly assuming that the middle point of the CCD is 0, 0, which means that my coordinates here are going to count from 0, 0 in the middle, just like I showed you. And I think that on the homework problem, I'm asking you to make that assumption, right? So that means that if I had, for example, a 800 by 600 image, that this point would be like minus 300, minus 600, or minus 300, minus 400, right? Instead of being 0, 0. So again, if you want to really convert it to Photoshop pixels, you'd also need to add kind of half the width and half the length to make sure you don't have like negative X, Y locations. Again, this is all just convention. It's not like rocket science, but it is something to be aware of, especially as you start to program image processing algorithms. You kind of want to make sure you're doing things in the right way. So just kind of be aware of that. Okay, so we talked a little bit about, I'm going to do pretty much all my class examples in MATLAB. I'm not against you. Oh, yes, question.
So for the pixels?
Yes.
So you have the center at a point, but then which square is that?
Oh, I see what you're saying.
So yeah, when you look at the pixels, are you looking at like location-wise or actual pixel?
Yeah, that's another interesting point. So we're kind of saying that I'm looking at this whole pixel as the 1, 1 pixel, right? And so kind of I think what you're getting at is that 1, 1 in the middle of the pixel, or is it at the corner of the pixel, right? So I think for the purposes of this, we can think of 1, 1 being the center of the pixel, right? It's not going to come up so often that you have to worry about it too much, but I see what you mean, right? So the way to think about this is that, I have an array of sensors, right? I'm going to call this sensor the 1, 1 sensor, and then I've got the camera aperture. All sorts of light is coming through, not like that, so like this. All sorts of light is coming through the aperture, because the physical sensor has some finite extent, right? And so fundamentally what's happening is that the 1, 1 value is like the integral over the sensor size of all of this illumination, reflection stuff corresponding to a whole bunch of little objects in the scene, right? And so, we're kind of thinking about 1, 1 as being this block. It's not even necessarily you have to worry about it being centered. Again, if you find yourself getting confused, just let me know. We'll figure it out. Okay. So we talked about, in MATLAB at least, I was saying that I'm going to mostly motivate stuff in MATLAB. When it comes to the project, to some extent the assignments, although I think it's not a bad thing to be able to use MATLAB for this stuff. One reason being that MATLAB has an image processing toolbox that is very well optimized to make your life a lot easier. There's lots of stuff built in. There's no need to do any for loops around image pixels like you might have to do if you were programming it up in C. But, ask me if you find yourself struggling with MATLAB somehow and you want to use something else. Especially for the project, that's certainly fine. But for the course assignments, I may ask you to use stuff in MATLAB. So we talked about imread. and imshow. I've been using kind of those already. And then imshow, where I specify the image, and then I say, you know, brackets like this. This basically says, you know, scale, you know, scale the smallest value to black and the largest value to white. We'll talk about this a lot more in the next lecture. So the next lecture we're going to kind of talk about, you know, image display and what are called point operations for taking the pixel value and showing it on the screen. You may find that you need to use this command, RGB to gray. We're going to talk about that more next time also. So a lot of times you want to do some image processing, you read in a color image, and then you try to apply some sort of grayscale operation to it, and it kicks back into an error saying this is actually a color image. So you can convert it to grayscale with this command. And that's even important for, you know, you may have a image that looks grayscale to you, but is stored as a file format as a color image with 3 color channels that if you were to drill down would probably be all exactly the same. So you have to kind of, you know, get rid of the 3 color channels and convert it to 1. So that's one thing. You can definitely do, you know, image processing operations, just like adding 2 images, subtracting images, averaging images. All that stuff is okay. But one thing that's important to remember is, again, this kind of difference between a MATLAB unsigned 8-bit integer and a double, right? And so let's talk about that a little bit. So we can close this up. Okay, so I can make, so actually this is a good time to think about how would I make an image, okay? So I think I did this last time, or did I, yeah, okay. So the idea being that, you know, let's make a ramp kind of image where I have, say, going from black to white, and I'm multiplying that by a vector of 1s like this. So that's like saying I have this is going to be a row vector, so I have to transpose it, and then I'm multiplying it times this row vector. So when I make an image like this, when I make a variable like this, at first MATLAB doesn't know any better that, you know, if I do whos, you'll see that, you know, the image that I originally read in, which is much bigger, this original thing called im, right? That's the picture of, that's the picture, I don't even remember this picture of. Oh, that's a picture of Dorf, right? So that image is a lot larger, but it's a uint8, whereas this image is a lot smaller. It's taking up almost half the size of this, but and the reason for that is it's a double. So if I want to make this like more like something that I would read out of a file, then I could cast it into uint8. It would have the same variable, it would have the same values, but it would take up a lot less space, okay? And if I were to look at that image, then I get this kind of smooth ramp, okay? And so let's make another image that is just the sideways version of this first guy. So I can do things like, so this is where you may immediately kind of run into some trouble, right? So suppose I wanted to take the average of these 2 images, okay? So there are a few ways I could do it, right? And many of these ways are not going to work for you the way you might expect the first time, right? So for example, let's just look at image 1 plus image 2 over 2. So I guess this actually doesn't look so bad. But I don't think actually this is fully the right thing. So let's just think about, how about this image? Let's try it this way. in theory, all these things should give me exactly the same thing. So let's look at these side by side. So here's the first guy I did, and here's the second guy I did. And these definitely look different, right? So why should they look different? Shouldn't they be exactly the same? Actually, the more I look at it, like if I look at this one image on the left, it almost looks like the whole lower triangle is actually just a flat gray color, right? That doesn't seem right. And so the reason for this is that you can't do operations on an 8-bit integer in the same way that you would with a floating point variable. Because anytime I complete an operation on a uint 8, it has to get turned back into a uint 8, which means it has to be in the range from 0 to 255. Anything that is below 0 is going to get turned into 0. Anything that's above 0 is going to get turned into 255. So what happened in the first case was that if I think about looking at the average, so if I think about the corner of the lower right-hand corner of the image, let's think about that. So that, here's a little kind of clever MATLAB notation. So this is saying, show me the 3x3 corner at the bottom of the image. Those are all going to be image pixels that are pretty close to white, right? Same thing is true for the other image I tried to add to it. And when I try to add those things together, it's immediately going to add those two numbers. It's going to get some bigger number than 255. It's going to clip that to 255, and then it's going to divide by 2 to give me 128, right? So even though I know that there should be kind of a series of numbers here, by virtue of the fact that everything has been done in this quantized world, I've got some problem, right? And so the safest thing to do, which is a little bit clumsy, would be to do something like this, where I'd say the average is equal to double M1 plus double 2 over 2, right? So now this is going to be a double, and if I were to look at this and say scale it from here to here, then I'm going to get something, I guess I should just avoid any conclusion. Then I'm going to get something that looks like my continuous ramp. If I were to look at the lower right-hand corner of it, I would see that since this is a double, I'm going to have continuous values, right? Some of which are, you know, fractional. And then if I wanted to, I could, you know, turn that back into a 8-bit integer like this. And so it's a little bit clumsy. And you can see that actually this, I'm willing to bet that even this set of entries is going to look a little bit different maybe than the other average I tried to do. You know, so here, the bottom one is what I tried to get. Remember what I did was this. I said, give me half the original image plus half the other image. The problem with this is that when I divide those 8-bit integers by 2, I'm losing all my fractions, right? So when I do that, I can't have an image pixel that is 67.5 if it's an unsigned integer, right? So that means that all that stuff gets rounded, and I lose like these little half pixel intensities here and there. So the moral of the story is just when you're doing things like combining images, be careful with making sure that you're not losing information. Now, I could be wrong, but you know, there are some built-in MATLAB commands that kind of take care of this for you in the sense of, I think that the thing that's going on under the hood is exactly what I just mentioned. It's probably taking things in double. So if you really feel like you need to have a MATLAB command, you can use this imadd command to do what I said here. So if you look in the image processing toolbox documentation, there's a whole thing about image arithmetic, which involves, you know, dividing and combinations and multiplies. That's going to do all the stuff that is fundamentally under the hood, just converting them to doubles, manipulating them, and taking them back, right? Okay. Another MATLAB thing just to kind of be aware of, and this is more of a general MATLAB thing than anything else, but it's good for this class, is that, suppose that I have some 3x3 matrices. So I have two matrices, right? And so we know that there's a difference between A asterisk B, which gives me some 3x3 matrix, and A dot times B, okay? Those give me two different 3x3 matrices, and in this class it's important to know what the difference is, right? So the dot times here is basically saying element by element, multiply the entries together, right? So for example, here, what I want to get is 8 times 7 is 56, 1 times 8 is 8, 6 times 3 is 18, so I should get 56, 8, 18 across the top row of this thing. That's often kind of what I want in image processing. If I want to kind of multiply point by point two images together, I need to use this dot asterisk. The regular asterisk is going to be like regular MATLAB matrix operation. The kind of things that you need to do a lot in other worlds, other classes, other electrical engineering things. You have to multiply these things as if they're, normal matrices. But in this class, often that's not what you want. You want to do the dot times. And so it's kind of important to remember what matrix multiplication am I trying to do. Often you will get, so if these things weren't square, then you wouldn't have a problem because if I have two different matrices, like a 3x4 matrices, I can't do A times B. It will tell me that those matrices don't have, their columns of one has to equal the same size as the rows of the other one, right? So you'll kind of know whether you made a mistake when you get an error like this, and you can say, oh, I can do A dot times B, and I can get what I want, right? So again, this is kind of just like MATLAB 101, but something to remember. Yep?
Is the reverse true? Like if you have a 3x4 and 4x3, you try to dot multiply?
Yes, should be. So like if I have A times B, A dot times B transpose, right? Should give me the same error, right? Yeah. The only problem is when you have square images, then you may have to be careful about which one am I doing, right? If you have rectangular images, it's probably really hard to get confused. Okay. Just a couple other miscellaneous stuff while we're talking. So you may find, we're going to definitely talk a lot about pixel processing in the coming lectures. And so one notation or one phrase that we're going to use sometimes is called the four neighbors of A. So if this is A, then the pixels that are directly adjacent to it, we call these four neighbors. And you may also hear me say 8 neighbors. That means that we look at the guys on the off diagonal as well. So again, if this is, just as an exercise, if this is I at pixel xy, then our notation is going to tell us that this pixel here is 1 less x value. This is going to be 1 more x value. This is going to be 1 more y value. This is going to be 1 less y value. Okay. We may also sometimes talk about distance measures. Not too often, but just to be worthwhile. So, for example, if I'm talking about distance, so I may say, how far is this pixel away from this pixel? It's 1 away in this direction. This pixel will be square root of 2 away because it's, got the diagonal. This would be 2, 2 square root of 2. This would be like square root of 5, and so on. So this would be like Cartesian distance, or Euclidean distance. I guess Euclidean distance is really what I mean. And sometimes you may talk more in a kind of a discrete world about saying how many steps it takes me, kind of like what they call a Manhattan block distance, where I say, okay, I have to walk 1 block to get here, 2 blocks to get here, 3 blocks to get here, 4 blocks to get here. And so basically, you kind of have a more call this the Manhattan distance, sometimes you see, or city block distance. And I guess the last thing I'll say, which is really, we're not going to talk a ton until maybe, several weeks about video, but video is a kind of a whole other animal, actually. So video, you also have to take into account sampling in the time domain, right? Which is kind of like the frame rate of video. I kind of alluded last time to the fact that there's a speed above which your visual system perceives a stream of discrete images as being a continuous flow of light, right? And so that's why, most video is going to be at something like 30 hertz or 60 hertz, right? And so we're not going to talk too much about that, but just to kind of emphasize there's a sampling issue in that direction too. And I guess the last thing, since we have a little bit of time, let me just show you one cool YouTube video that I came across. Which I should have bookmarked. I don't know why. What am I using Yahoo search for? Oh no. Something must have gotten screwed up. Yeah, let's see this one. Ugh. I have a feeling that something bad happened to my browser settings. Let's try this instead. Okay. All right. All right. Watch this ad. Oh, see, it's even relevant to you guys renting textbooks. Good job. Okay, so just skipping through this a little bit. I thought this was cool because you could actually see what happens inside the camera when. So this is actually like an old school. So again, this is a photography thing, right? So an SLR camera, right, the analog SLR camera, has basically a mirror in it that if you're looking through the viewfinder, it's reflecting to your eye what you expect to see when you take the picture. And when you press the shutter, that mirror flips up out of the way. The imaging surface is exposed by the shutter, and then the mirror flips back into place, right? And so this kind of ka-chunk that you had when you had an old school analog camera was this mirror flipping around. And DSLRs still have this mirror. And so here, what you're going to see is basically a slow motion of the mirror. Well, first you're going to see this guy. So you see the mirror kind of flipping up out of the way. And then the shutter comes up, exposes the film, and then comes back down. And then the mirror closes, okay? And what's kind of interesting about that is that if you have a very rapid exposure image, so here what you're going to see is basically what happens at different shutter speeds, okay? And so the faster the shutter speed, the less time that imaging surface, the sensor surface, is actually physically exposed to light. And what you're going to see actually is that there's actually a strip almost that rolls across the sensor. So not all the sensor elements are getting light at the same physical instant of time. So if you look at the lower right-hand corner, you can see that after this thing flips up, when you have a very fast, or I'm sorry, maybe the upper left-hand corner, when you have a very fast shutter speed, let me wait for it to go here. Right? So what you just saw here was that actually there's only this very narrow strip of light that is exposed, and it kind of rolls across the imaging area, right? So it's not like the imaging area is fully open to light all at the same time. And that has some implications for, you're not actually physically getting a snapshot of the same scene at the same time. And in some sense, that's what leads to things like, motion blur and weird shadows. So it's actually worth, I'll post this on Piazza. It's actually worth watching this video a little bit. Like here, I think what they're making the point of is that, when you have something that's very, very fast moving, right, that the cork in this example is moving faster, and that's why even though the cork itself is got a flat top, the fact is that the cork is getting imaged at different points in its flight as the little sliver of opening rolls across the shutter. And so it looks like it's got this slanted top to it, right? And I'm sure that you guys have probably seen the kind of goofy tricks you can do with your smartphone, right? Your smartphone definitely also has this kind of rolling shutter where different segments of the image are getting pulled at different times. And so that means that if you take a movie with your phone or take a panorama with your phone and move it as you're going, you can make really goofy, elongated effects that look really strange. And a lot of that is due to the fact that the image is not all coming onto the sensor at the same time, right? But I didn't really, I don't think I'd ever actually seen it illustrated that fast until I saw this video. So again, it's interesting stuff. Okay, any more comments or questions? Yeah. Yes, you're talking about these slides. Sure. I mean, so I have this PDF. So this is I can post these separately, and they're kind of integrated into my notes, but I can put those alongside too if you want. I guess I can just tack this on to the end of the written notes. Sure. Other comments or questions? Yeah. Yeah. Yes, right. So the question around video on the homework, I forgot about that. Right. So that's exactly right. So you basically say I've got how many bits is every single image taking up, and I multiply that by how many frames I have to have for the whole movie. That's right. Other comments or questions? Yep.
The homework question number 4 says 2 watt pixel, the word coordinates project 2. I haven't done the calculation, but what if it's project to the border of the
Right. So that problem is set up to be sure you should get something that is inside the CCD, right? Yeah. So don't worry about that. If you do it right, you should be inside the pixels. Right? And don't forget to probably round the pixels after you figure out where they're rated, right? Because we can't have pixel 3.5, 4.8. You've got to actually get an integer number of pixels. Yep.
Should we be truncating or just?
I'm not going to be too worried about that. I think just round to the nearest pixel is fine. Okay, so I have office hours this afternoon as usual, and see you there. Have a good weekend.